induced voltages and inductance. Magnetic flux. Okay. In chapter 4, we learn about electric flux, which is also known as lines of electric field. In similar concept, we can say that magnetic flux are lines of magnetic field. Now, in this topic, we are going to learn about what is magnetic flux and how the change of the magnetic flux can create electric current. Alright, so magnetic flux can be calculated by equation pi equals to BA cos theta, where B is the component of uniform magnetic electric field B perpendicular to the plane of the loop. Okay, theta is the angle between magnetic field and the normal of the loop. Alright, and A is the surface area. Alright, so let us analyze how electric flux is defined. Alright, okay, so let's say we have a plane or a surface area here. Alright, and let's say we have magnetic flux penetrates into the surface area. Alright, so this green arrow represents magnetic flux. Alright, now first we need to know that every surface area they have their own normal line. Alright, so this dashed black dashed line here is the normal of the plane or normal of the surface area. In figure 20.2a, we can see that the normal of the surface area is making an angle theta with the magnetic field. Alright, so at figure 20.2b, alright, in the other side, okay, we can see that the normal here is making theta with the magnetic field. Alright, so here we can see more clearly. Alright, in the other view, okay, let's go through the other diagram. Alright, so here is the plane, a plane, okay, a plane which is perpendicular with the magnetic field. Alright, okay, so this is a plane. Alright, and you can see that the normal, let me draw the normal of the plane here. Alright, so this is the normal of the plane. Right, this is the normal of the plane. The normal of the plane is parallel, okay, to the magnetic field. Meaning, the normal is making 0 degree with magnetic field. Alright, so what is the flux here? Flux equals to BA cos theta. So since it is parallel, then the normal is making 0 degree with magnetic field. Right, so cos 0 equals to 1. So we can see that from the diagram here, there will be maximum flux hitting the surface area. That's why we get pi equals to BA. Alright, you can see that the arrow, the green arrow here, which represents the magnetic field, hit, okay, the surface area in a maximum value. Alright, with the maximum value. Right, compare with the other diagram here. Now here you can see that the plane is parallel with the magnetic field. Thus, its normal is perpendicular to the magnetic field. Alright. Now, since the normal is making 90 degree with magnetic field, then we can say that cos 90 equals to 0. So what can we conclude here? There is no flux hitting the surface area here. Alright. So there will be the flux equals to 0. No flux hitting the surface area at this position or at this orientation. Right, let's go through one example here. Okay, a conducting circular loop of radius 0.25 meter is placed in the xy plane in a uniform magnetic field of 0.36 Tesla that points in the positive z direction. Alright, so this is the plane. Okay, the circular loop that lie along xy plane. Alright. Okay. Now, the magnetic field is directed along positive z direction, along positive z direction. So the question is to calculate the magnetic flux through the loop. First, let us identify the normal of the circular loop. So the normal of the circular loop lies upward, isn't it? Lies upward, alright? So it is making 0 degree with magnetic field. So we have theta cos theta equals to 1. Alright, so we have pi equals to BA. A is the cross-section area of the loop, which is equals pi r squared. Right, substitute r, which is 0.25 meter. Okay, then you get the cross-sectional area of the loop. And substitute B, which is 0.36 Tesla. Alright, so you get the flux is 0.0706 Weber. Okay, Weber is SI unit for magnetic flux. Okay, B. Suppose the loop is rotated clockwise around x-axis. So the normal direction now points at 45 degree with respect to z-axis. Alright. So in part B, we rotate the plane. Okay, we rotate the plane so that the normal is making 45 degree with magnetic field. So it means something like this. Alright. So this will be the normal. Alright. So now the normal is making 45 degree with magnetic field. Alright. So you just substitute theta equals to 45 degree. Then you get the new flux. Okay. Part C. What is the change in flux due to the rotation of the loop? Alright. So to find the change in the flux, we just subtract the value, okay, from A and B to find the difference. Alright. So basically, in this topic, alright, that I have mentioned you earlier, okay, the change in the flux will create electric current. Alright, as you can see from this diagram, alright, here we have a battery. The battery is connected only at primary coil. Okay, there is no battery connected to the secondary coil. Alright, and these two coils, okay, they are wrapped along a insulated iron, meaning there is no connection between primary coil and secondary coil. Okay, logically, there will be no current at the secondary coil. Alright, now when the switch is closed, when the switch at the primary circuit is closed, alright, so what happened? Okay, current will pass through the primary coil. Alright, as we have learned in the previous chapter, there will be flux. Okay, sorry, there will be magnetic field produced at the primary coil. Alright, so because of the change in the flux here, because before this no current, then we have a current, so there will be change in flux at the primary coil, isn't it? From 0 to the existence of flux. All right, so there is a change in the flux at the primary coil. Okay, because of the change of the flux here, there will be an induced current at the secondary coil. So we can see readings at the ammeter. All right, so the observations that we have from this simple experiment, electric current could be produced by changing B. Alright, so induced EMF is produced in the secondary circuit by changing the flux at the primary coil. Okay.